I passed out a chart to you that this is kind of going to be a go-to page in your notes. Kind of every derivative shortcut that we've discussed, we're going to go ahead and write it down. And then after we review those shortcuts, we're going to do a graphing activity on the back. Okay? So let's go ahead and just discuss kind of these shortcuts we've had so far. If we have a polynomial function x to a power, how do we find the derivative of that? And maybe we can describe it in words, maybe. Yeah?
Multiply down the power, and then take the power and subtract 1.
All right. So mathematically, we would multiply down the power and then subtract 1 from the power. Good. Okay. All right. So in words, we'll go ahead and say multiply down power, subtract 1 from power. That's nothing new to us, right? That was kind of the first shortcut we talked about. What about product rule? What would the derivative look like, our little shortcut? And then maybe we'll write down a phrase or wording that we use to help us remember it. Yeah?
I think if I remember my trick correctly, it was 1d2 times plus 2d1.
Okay, so we'll write that as our little phrase, 1d2 plus 2d1. And if we were to actually apply that to these two functions being multiplied together, maybe you want to label them 1 and 2. We would have h of x times g prime plus g of x times h prime. All right, what about quotient rule? Either what the derivative looks like using function notation, math language. Maybe you want to give some type of phrase or wording we use to help us remember it. Liam, can I come to you for this one? There we go. Low d high minus high d low, square the bottom, and away we go. All right, so applying that wording, that shortcut phrase to our functions, we would have g of x times h prime minus h of x times g prime all over g of x squared. We doing okay so far? All right, chain rule. Either, bless you, either wording we kind of use to help us find the derivative. Maybe you want to find the derivative using the math notation. How does a chain rule work? Yeah.
Derivative of the outside with the same inside.
Okay, so derivative of inside, or sorry, outside, you said. Yep, that outer layer. Good. Derivative of outside, and then you said you keep the inside. Yep.
And then multiply by whatever is the derivative of the inside.
Times derivative of inside. Okay, so we keep taking derivative of these layers one at a time. But we got to make sure as we're taking the derivative of the layers, we keep the inner layers because we haven't really touched or used them just yet. So in terms of math notation, you want to give it a shot, Ryan? Go ahead.
This would be h prime of g of x.
Yep.
Multiplied by g prime of x.
There we go. All right, so the derivative of the outer layer would be h prime. Notice how we keep the inner layer, that g of x, and then times the derivative of the next layer, in this case the inside stuff, which would be g prime. Pretty good. All right, so those were kind of like the shortcut rules we had, where we had some type of phrasing to help us with those. Then we got to more specific derivative shortcuts for particular functions, like exponential shortcut, logarithm shortcut. We had trig function shortcuts. So these are the ones that we just have to know, like this is how they always look. So what about an exponential function? How would you find the derivative of e to some power? We did something like this yesterday. I'm wondering if we kind of remember, haven't forgot it. Yeah?
Basically copy the equation down.
Okay.
So e to the d of x.
Yep.
And then multiply by the derivative of power.
There we go.
D prime of x.
Perfect. All right, so maybe in words, the derivative of an exponential, you keep the exponential, then times derivative of the power. I'm using the letter D to represent derivative just because I don't really have a lot of room there. I don't know how small you guys want to write. Okay. What about if we had the natural log of something? Like the natural log of x, the natural log of sine, the natural log of x squared plus 2x plus 3, whatever's on the inside here. You can make it be whatever you want. How does that derivative shortcut work? You're on a roll, yep.
If I remember correctly, it's just the function inside.
That's part of it, okay? The inside part.
Oh yeah, and then that is below the derivative on the top.
Of the inside. There we go. All right, so in words we can say derivative of inside divided by the inside. Okay, so the natural log in this case is just signifying that you have some type of fraction, and in that fraction you have the derivative of the inside divided by the inside. So far so good. All right, what about our trig function shortcuts? I'm just going to have to say you have to know these. Okay, there's no really way for us to describe them in words. We just have to know the derivative of sine is this, the derivative of cosine is this. All right, so can we list them? Derivative of sine. We got cosine. Derivative, maybe I'll label these 1, 2, 3, so that they're corresponding to something. All right, derivative of sine, cosine, derivative of cosine, yeah.
Derivative of cosine is negative sine.
Negative sine, all right. Derivative of tangent. Maybe we'll come back to that one. Derivative of cosecant. Maybe we'll come back to that one. Derivative of secant. Maybe we'll come back to that one. Derivative of cotangent. We'll come back to that one too. All right, so we covered these in the quotient rule section, where we rewrote tangent as sine over cosine, and then we went through low d high minus high d low. Okay, in the end, we ended up with a secant squared x. And what's nice is the derivative of cotangent is very similar to this, but instead of secant, it's cosecant squared of x, and it happens to be negative. Okay, all of the trig values that start with c have a negative derivative. We kind of saw that yesterday, right, with the inverses? Okay, the same thing's happening with the regular trig functions too. The cosecant and secant are the trickier ones of the bunch. The derivative of cosecant, since it starts with a c, the derivative is negative. And the derivative is cosecant cotangent. For the derivative of secant, it's very similar to this, just kind of the reverse trig functions. It would be secant x tangent x. Alright, so I know we're good on 1 and 2, like sine and cosine, but we've really got to let the other 4 sink in as well, okay? Then we got to inverse functions. And this is where it was a little tricky. The derivative of an inverse, we said was the reciprocal, so 1 over the derivative of an original function evaluated at the inverse corresponding point. Okay, so mathematically that's what it looks like, but in class we kind of discussed 3 steps to help us figure out the derivative of an inverse. So in terms of the wording, I want to write down those 3 steps. Can we think back to a few days ago? What do you think, Liam? Oh, we'll get here in a second. Okay, we'll get to the inverse trig in a second. I'm thinking about these steps. Yeah. You've defined the other one, right? That corresponding number. So we'll say find corresponding, I'm going to abbreviate, find corresponding number. So they're eventually going to give you an x value for the inverse, but if that number is an x value in the inverse, it's a y value in the original, so you have to use that y value to figure out the corresponding x value. Craziness. We did a lot of table jumping. So we find the corresponding number. What do we do after we find that number? That other x value. So we find this, and then if you look at the notation, we then have to figure out the derivative of the original function evaluated at that number. So we'll say derivative of original at this number. So in that aspect, we would have some number left down here, which means we just have to reciprocate it. Okay, so reciprocate answer, aka 1 over that, and we'll get the derivative of the inverse. Because we saw, okay, based off of the inverse graphs, that if you were to go to corresponding spots on the graph and analyze their slopes, they would be reciprocal values, not opposite reciprocals like normal lines. Okay, just reciprocals. All right, so there's a good kind of shortcut chart explanation for inverse function derivatives. All right, what about the trig ones? Now I know we went over 6 of them yesterday, but I told you arcsine and arctangent are kind of the 2 big ones. Liam, you want to tackle one of those you tried before? There we go. Okay. So that's the arcsine derivative. What about arctangent? It's kind of similar. It's another fraction. There's just slight differences. Bless you. Yeah. Yep. Bless you. There's no square root in this one. X squared plus 1 or 1 plus x squared. Yep. Either way you want to write it. Good. Alright, so just like the other trig ones, I'm just going to have to say you have to know these. Okay, there's no really wording or process for us to describe. So here's a nice go-to chart with every single shortcut we've discussed. So if you have trouble finding a derivative, maybe reference this chart to help you out, okay? I think it's a good resource. Alright, we're going to flip the page and we're going to practice kind of a matching activity today. On this page we have a bunch of original functions on the left-hand side and a bunch of derivative graphs on the right-hand side. We're going to try to match which original function is paired with a derivative on the right. So let's go ahead, we'll try maybe a few of these together and then I want you to try some of them on your own and we'll see how we do. What are some things we can analyze on an original graph to help us figure out something about the derivative? What do you want to look for? Yeah.
We could look for relative or absolute maximums and minimums.
Maximums or minimums. Okay, so notice how on this graph we have a minimum at the x location of 0. So what would the graph of the derivative look like at this x location of 0? Yeah. Well, so this tangent line is horizontal, which means the derivative is 0. So on a derivative graph, where would that point value be located? Where's a point value of 0 found on a graph? Yeah. On which axis? The x-axis. Okay, so at this spot, at the origin, we need to have some type of x-intercept. Okay, we're going to be on the x-axis. Something else you can look for is what type of graph or function is number 10? Can you give me a name? Yeah.
Parabola.
It's a parabola, so it's a quadratic, right? If you took the derivative of a quadratic, what would it turn into? Yeah. A line, a linear function. Okay, so maybe we'll use that concept to help us narrow down our different options here. So if you take a look, let me zoom out for a second. If you take a look on the right-hand side, we know the derivative graph should be a line, okay, and a sloped line because a horizontal line is considered a constant function, not necessarily linear. So our only options look like L and M and I, because aren't those the only linear ones? So of those options, we need to have a graph that has an x-intercept at 0, because that's where we had a max or a min on the original graph. So it looks like that concept would eliminate M, because notice how the x-intercept is over there on the right-hand side, not at 0 like the other ones. Okay, so out of all of these, we narrowed it down to 2. What else can we look for on this graph to help us pick the correct one? Yeah.
We also know that the right half is the graph is increasing, so the derivative should be positive.
Right, and the left half is negative, or decreasing, right? So the derivative should be negative. So graphically speaking, if the derivative is negative, it should be below the x-axis, and if the derivative is positive, it should be above the x-axis. So between those two options, notice how we're below on the left and above on the right for I, whereas L is kind of switched. So for number 10, we would say that the respective derivative graph is I. Okay, so if you want to, maybe we'll put just like a big X right there for that one because we already counted it. Maybe we'll try 11 together as well. Okay, what type of function is 11? Yeah, cubic. If you take the derivative of a cubic, you're going to get a quadratic. You go down a degree, and a quadratic looks like a parabola. So out of your options, it looks like we have G and P. That's nice. Maybe we can take a look at some maxes and mins. we have two maxes and mins, so that means we need two x-intercepts on the derivative graph, one on the left and one on the right. And between our options, it looks like G is the only one that fits that concept, right? Okay, so it looks like 11 has to be G. Do we want to keep trying some together, or do you think you can maybe tackle some on your own? Okay, go ahead and try some on your own. You can work together, work by yourself. I'll be around to help, okay? But keep on analyzing the graphs, thinking about what would the derivative look like. Bless you.